Non, c'est n'importe quoi, comme je dis, c'est n'importe quoi. Alors que voilà, je sais pas. Alors là, ça remonte.
Hello, hello everyone. Can you hear me in Teams?
Yes, we can hear you.
Okay, so I started the recording again, and we are going to continue with the last tool from Intel One API Toolkit. Okay. Okay, so the last tool is Intel Trace Analyzer and Collector. As I told you at the beginning of the class, this is the tool that you are supposed to use when you are programming in distributed memory environments, and actually is especially indicated when you are programming with MPI, and is very focused on MPI. So if in parallel programming you are now with the MPI part, I believe that this tool can be very useful for you. So the name of the tool is Intel Trace Analyzer and Collector, and is usually referred in all the websites from Intel with the acronym ITAC, ITAC, okay? So wherever you see ITAC, they are talking about this tool. And it's actually separated in two parts. One is Intel Trace Collector, and this tool is just used to generate the trace of the execution of the program when the program is running. And once you have generated the trace, you use the second tool, which is Intel Trace Analyzer, to visualize the output of the analysis, okay? So there is another subtool, which is called MPI Correctness Checker, that we are not going to see here. Can you put the mask? Yes, hello. Okay, so this only checks if the MPI interface is correct or not, okay? So for it's very common, and you are already experiencing that in parallel programming, that when you use the MPI API, sometimes you make a lot of mistakes with the parameters and things like this. Okay, so if you pass an MPI program to this subtool from Intel Trace Analyzer, it's going to tell you if you have made any of these common mistakes. So when you parallelize programs in distributed memory, and this is a small review, you have like different options, and the most obvious and the most widely used in HPC environments is MPI. Okay, there are other alternatives such as UPC, okay, that is a PGAS language that tries to make the programming of a distributed memory system as easy as in shared memory systems. But actually, when you use UPC, normally, not always, the runtime is built using MPI. Okay, so although you are using another language or another library, sometimes the underlying technology that you are really using is MPI itself. So these programs can also be profiled or studied the performance using this kind of tool. And the same happens with application purpose alternatives such as Hadoop. Okay, so Hadoop is for big data, and some implementations of the implementation of Hadoop use MPI, I believe, as the underlying technology. So how to generate the trace with Intel Trace Collector? There are two alternatives with executing the code with MPI run. You know that when you run an MPI program, normally you do it across a launcher, which is called MPI run, to which you can pass several parameters. So in this case, if you pass the parameters, dash trace, this is option 1, okay, for generating the trace. There is a second possibility, which is passing a flag called tcollect. But the difference between one and the other is that this option is going to generate a smaller trace with less information, while this option is going to instrument all the code from the user, your own code. So you are going to see in the analysis reference to your own functions, okay? So obviously this is more verbose, and this is going to generate a bigger trace. So the consequence of this is that you are going to have a bigger overhead during the execution or the generation of the trace, and that you are generating larger traces. Okay, so the main components of the analyzer, that is the other side of the tool, Intel Trace Analyzer, is to find bottlenecks. So you are going to see a graph or an illustration like this. This is the most important one. It's called a timeline. So this is time. And, sorry, this is time. And in the y-axis, you are seeing MPI processes, okay? And in different colors is going to be represented the computation in each node. I believe this is blue, okay? And then in red, in this case, you have the communications. There are other illustrations or other views of the behavior of your program, okay? But I'm going to comment it later more in detail when we open the tool here. You have a performance assistant, as it happens in other tools like VTune. So if it detects an important problem in your implementation, it's going to inform you about that, and it's going to give you advice, as it happens in Advisor and VTune, about how to improve the code. Also, we have the MPI checker, okay, that detects different problems with MPI, like deadlocks, possible data corruptions, or errors in the parameters of the different function calls. And the Intel Trace Collector API is an API that allows you to put function calls in your own program to give more information to the tracer. Okay, this is a more advanced use, and probably you are not going to reach to this level of expertise using Intel Trace Analyzer. But the idea is that using this API, you can label together groups of processes, okay, that make different functions, or you can define ad hoc performance counters, okay, user-defined, not those that are already available in the tool. Okay, so this website have good tutorials on Intel Trace Analyzer and Collector. And okay, first, before you do this, I'm going to make a sample execution, okay, of the analyzer and the collector. Let me close this. Okay. Okay, I put in the chat a file which is an implementation of Poisson in MPI. I'm going to download the code. Okay. I'm moving it into a directory. Okay, and first I have to check that the MPI compiler that I'm going to use is the Intel one. Okay, so as I source set bars before from YAPI, this is the case. And also I can check MPI run. Okay, because sometimes if you have installed OpenMPI in your computer, if you don't make sure that you are using the Intel one, these commands are not going to work. Okay, so you have to make sure that you are using the right compiler and the right MPI runner. Okay, so I enter into the directory and I'm going to compile this code. I believe that I have to compile it with dash trace. Okay, so this generates the binary. And now, okay, this is a very fast execution. As you can see, it's already generating the trace. Okay, the STF file and all the other files are the trace, and they have information, so this works correctly. Okay, but if instead of trace I do tcollect, no, this is not working like this, because I don't know if the tcollect option works anymore. Let me check. What is happening? No. Okay, so just with ttrace. Okay, so this is running the code. And now I can open the trace with Trace Analyzer. Okay, and you have like different views. The first one is always a summary, and what you can see is which percentage of the execution time was the serial code, which percentage are to MPI calls. Okay, this was very quick, obviously, so it's not very time consuming. Maybe we can change that a little bit. Okay, let me try again to change the size of the computation, because hopefully it's going to be easy. Okay, so instead of this one, I'm going to put like this, the size of the problem. Okay, so I'm compiling the code, running again, which takes a bit longer, not too much. No, it's not. It didn't change. Okay, never mind. I'm going to open the trace. So you can see the duration of different types of MPI calls or reduce. I believe that you already know this one. This is a reduction that happens in this case at the end of the computation, the sends, the receives, etc. If I press continue, okay, what I see are different kinds of information, but okay, in charts, I can activate an event timeline, okay? So this code is executed among 4 MPI processes, and what you see here is that at the beginning I have some user code, probably some kind of initialization, okay? And at some point I have red code that are MPI communications, and the lines, the black lines that you have here are the communications itself, okay? Probably this is not very useful like this because you see too much information, so you can narrow and make a zoom, okay? So you can get a better view of what is happening, okay? So apparently you have communication between different processes, and then they compute, they communicate, the usual behavior of a MPI program. You can make a qualitative timeline, okay? So the idea of this is that you can show, for instance, how many messages there are per time unit, okay? So this can be useful for you or can be interesting. A qualitative timeline is telling you at each point what is the y-axis. Okay, sorry. Okay, it's maybe the number of events of any type that are happening. And then you have the message profile, this one. Sorry. No. Okay. In the message profile, you see the 4 processes in this case, and you see in a darker color the communications that are heavier. So, for instance, you can see that there are communications between P0 and P1, between P1 and P0, obviously P1 and P2, okay? And the darker the color, the more communications you have, okay? So I don't know at which point of MPI you are right now, but normally you have different concerns when it's up to the performance of your MPI program. One of them is how well work is balanced among different processes, okay? So if in the timeline, let me put the timeline again. In the timeline, you see some of the processes, one of the processes to do less jobs than the others. Probably this is a sign that you are not balancing correctly your work, okay? Also, if you have too many communications and you believe that maybe these communications are too frequent or they can be unnecessary, you can try to improve that. Okay, you have more advanced things. One important is the imbalance diagram. In the imbalance diagram, you try to compare the work balance among processors of your implementation with respect to the ideal one. So the first thing you have to do in order to make this comparison is to create an ideal work balance. Okay, so this is what is asking to me right now. I'm telling to create it. Okay, so you can parameterize this ideal behavior. So after you start, this is the ideal. As you can see, it's the same name, but with ideal. Let me close it. And now I believe that I can make the imbalance diagram. Okay. So I can make the comparison between MPI and MPI ideal. Okay. Well, there is some information missing here because waiting. Okay, so in this case, it's telling me for MPI that the interconnection weight for MPI is 93%, it's a lot, with respect to the total execution time. Okay, so but in my case, when I check this in my own computer, when I put my mouse over one of these colors, it told me where these colors were about, what these colors were about. Okay, so basically, one of these bars, one of these colors were how much imbalance there were between one process and another. Okay, and in this case, I believe that it was quite low. I don't know why it's not showing this information here. Okay, so this is what you can do in local. If you want to do this in a remote location, what you should do is to connect to DevCloud. In DevCloud, I already have the MPI Poisson program, okay, because I tried this morning, and I have the trace also. But basically, as I told you before, you have to recompile the program for this machine. Sorry, no, it's not trace. Okay, and now I'm going to ask for a single node. Okay, and I enter in MPI and I run the program in the computing node. Okay, so now I exit from the supercomputer, well, from DevCloud in this case, and I have to do the same than before. That is SCP from DevCloud, from MPI, recursive, just to copy the whole directory, to here, okay, to the local machine. And once I have the trace in the local machine, I can open it locally and see it locally, okay? That is what I want to do. Sorry. Trace analyzer. No? Okay. The problem is okay, and this is the same execution that I did locally, but done in the DevCloud machine. Okay? If you use this for your parallel programming class, your teacher is going to love it, okay? Because it's something good to do. Because if you are able not just to program something and not to care about how it was, but also make some kind of analysis about how well it's doing, okay, I believe that the teacher is going to love that you are able to do this kind of analysis. And if you learn to use these tools for this subject, I believe that is something that you can take advantage to employ in another subject. Okay, so now in the rest of the class, what you can do is try this tool, but I'm also going to introduce the final task of the subject. Let me check if I remember my password. No. Okay, let me check. Which is my password? Wow. This is a complicated one. Okay. Just 1 minute. Okay, that was it. So in HPC tools, you have in the sections assignments in Aula CESGA, the final assignment. What you have to do is to get your code, the running example, the running code that you have in this subject, and to check your serial implementation with Valgrind, or you can use also Intel Inspector if you want, okay? So the reason for doing so is to find memory issues in your programming, okay? And then you have to write a report about what you found, okay? If you found that everything was all right, and that can happen, you have to say just that it was all right, okay? Then, once you have a sequential good code that is working correctly, you have to make a parallelization of this code using OpenMP, okay? If you use just a parallel for, and it's legal to do so, it's okay, okay? You don't have to think it too much. And so you have to write in the report how you parallelize the code, how much faster is the parallelized code than the serial one, okay? And then after that, you can use Intel BTU amplifier to make the usual analysis, hotspots, hardware issues, etc. Okay, and you have to put in the report screenshots of the output and which analysis you did from the code starting with this analysis. Okay, or more importantly, if you took any improvement or optimization decision depending on the output of this analysis. Okay, and then you can use Intel Advisor to see what is the output of Intel Advisor. If it tells you how to vectorize better your code or how to improve the vectorization of the code, and again, in the report, you have to include all this information, okay? And then, as a fourth point, you can make use of any other tool among those that we have seen in these 2 days, and also with Emilio, to improve the performance of your application, okay? So what do you have to deliver? You have to deliver a PDF of more or less 2 pages, okay, with all this information, including the repository, the address of the Git repository where the final code is available, okay? And in the report, you have to include all the information about this analysis and how you progressively improve the performance of your application. Any questions about this? The deadline is the end of October, 31, it's Sunday, okay? But if you want to finish on Friday, it's okay. Yeah, no, just one document, the PDF. Yes, and the PDF has to include the address of the Git repository. So the
and all the screenshots that ones using Intel one.
Yes, that must be included here. But you have a pending task with Emilio about filling a form with times of compiling your code with ICC. That's a different task. In this task, you have to report only on these topics. about how you use these tools to improve the performance of your application. Okay? No? No. So you have an application now that is sequential. It's not parallelized. So the first thing you have to do is to use Valgrind or Intel Inspector to check if there are any memory issues in your program. After that, you are sure that your program is working correctly. So you are going to parallelize it, okay, with OpenMP. You don't have to make a big effort in the parallelization because it's not the subject of this course. So you can put just a parallel for something like that, okay? And then after that, you are going to use different tools like Bitune, Advisor, whatever, and every time you use any of these tools, you have to put the screenshot of the output of the analysis or several screenshots, whatever you want, and also to write what you see in this output and which decisions you made according to what you see in this output. For instance, if you see that your main loop is not parallelized, an advisor is telling you to activate a compiler flag or to put a pragma in the code to help the compiler, you say, okay, I checked this, so I did this change in the code, and I saw that this improved the performance of my code, okay? So this is the kind of discussion that the PDF must contain. All the efforts that you made using the tools to improve the performance of your code, okay? Okay. No, no. If I say that, it's 2 and 1. This is the final. Yes, there are only 3 assignments. But there is an exam in January. Yes, an exam with Moodle, okay, with questions and things like that. But Moodle, what is PCM? It's a quiz, a quiz. Yes, yes. Like you have one question, several answers, and you have to choose the right one or just to fill a test. Okay? Okay, any questions? No? From teams, do you have any questions about the assignment? Okay, so I'm going to be here, okay, 1 hour more. So if you want to work on this or in the final assignment and you want to start with it and you want to make me questions during this time, I will be the first. Okay, you are going to start with the final assignment. Okay, it's okay to do so. What is the second? Yes. Ah, okay. You have, yes, it's true. I saw that you have still 1 week. If you want me to help. Shut up. If you want me to help you with task 2, I can do it also. Okay? Because now you have installed ICC in your own computer, so maybe it's easier to do so. Okay. Okay, so those in Teams, if you have questions, please send them to me through Teams, okay?
Okay.
Okay,
Hello, Diego. Can I ask you a question? Bueno, ¿te importa si pregunto en castellano?
Sí, sí.
Bueno, me he instalado todo, lo que pasa es que siguiendo tus mismos pasos, especialmente en esto último para el Trace Analyzer,
Sí.
no, cuando ejecuto la aplicación con el PRAM no termina.
No termina, pero te pone que va a generar la traza.
Sí, pero no termina.
Eso me pasó a mí. ¿Tu equipo tiene un procesador AMD?
Sí tiene, sí.
Vale, pues puede ser ese el problema, porque yo en mi equipo local, en mi equipo que tengo en el despacho, que tiene un procesador AMD, también observé ese comportamiento. Es decir,
Ya.
te ejecuta, te dice que va a generar la traza, pero la traza nunca se genera. Y el programa
Exactamente.
se queda colgado. Entonces, en tu caso, lo lógico es hacerlo en DevCloud.
Sí, era lo que estaba pensando. Y luego con el... Bueno, el ICC tampoco tiene el CPU dispatcher este mágico y no ejecuta nada vectorizado en el procesador de AMD tampoco.
Claro, claro, es que a mí me pasa lo mismo en el ordenador de despacho. Como tengo un procesador AMD, muchas de estas cosas no me funcionan. Y tampoco me dice por qué, ¿sabes?
Ya, claro, claro.
Entonces, bueno, en tu caso, como me pasa a mí, pues ejecútalo en DevCloud.
Vale, perfecto, muchas gracias.
De acuerdo. Sí. Vale, pues any other questions that you have, you can make them through Teams and in your case here, okay?